Lecture 11, Binomial Distribution. In this lecture, we will learn if a probability experiment is a binomial experiment, and we will find the exact probability for X successes in n trials of a binomial experiment, and the mean, variance, and standard deviation for the variable of a binomial distribution. A binomial distribution is a discrete probability distribution of a random variable that appears in a binomial experiment. So what is a binomial experiment? So a binomial experiment is a probability experiment that has independent n trials, and each trial has two outcomes. So a binomial experiment has this property. It has n trials. Each trial is independent of each other. It's independent. 1, 2, and 3. Each trial has two outcomes. We can call it success or failure. Now, for the official definition, the formal definition, we use success and failure. But in the question, it might be different. You can choose anything for success, or it will change in the questions. So let's look at the notations for binomial experiment. So one important thing is the number of the trials, and the second thing is the probability of success, which is P, and the probability of failure in a single trial, it's Q, and X, the number of successes in n trials, so it might be 0 or n value between 0 and n, and n minus x is, of course, the number of failures in n trials. Now, suppose the random variable x denotes the number of successes in a binomial experiment. Then the probability of having exactly x successes in n trials is given by this formula. This is the probability formula for finding the probability of x successes here. Little x, it gives the number of the successes in n trials. So here, this one is the n choose x, and it can be calculated by this formula here, and you can use your calculator. And p to x, p is the probability of success, and here what is q? Q is the probability of failure, and we know this q is like 1 minus p, by the way. We already know that one. Now x is here the number of the successes, x, number of the successes, and n is, we know the n is n trials, the number of the trials is n. So we can use this formula to find the probability if x is a binomial random variable. So x is called here, in this case, x is called a random variable, and probability distribution is of x is a binomial distribution. Why? Because the experiment is a binomial experiment. And we write, we say the random variable x follows a binomial distribution, and we say it this way. We say the random variable x has a binomial distribution with n trials, with this probability p is the probability of the success. Now, in order to apply the probability formula for binomial random variable, we have to make sure that this is a binomial experiment. So a binomial experiment is a probability experiment, and it has to satisfy the following conditions. One, the number of trials should be fixed, and each trial has only two possible outcomes, success or failure. Each trial is independent, and the probability of the success and the failure must remain constant for each trial. And the probability of failure is can be found by 1 minus p. And of course, the very basic ones are the head and tail issue when tossing a coin. Now let's look at here. In an experiment of tossing a coin 3 times, suppose we want to find the number of heads appearing over 3 tosses. Is it a binomial experiment? Indeed, yes, because uh, there are fixed number of trials. This is 3. We toss it 3 times, and there are only 2 outcomes for each trial, head or tail. And the trials of experiments are independent of each other. When you toss, each toss, they do not affect each other's probability. And the probability each time of success, if you define success as head or tail, it doesn't matter. The probability of head or tail is constant, it's 1/2. And if you say success, one of them, tail, let's say, it's 1/2, and then head, failure, it's again 1/2. So the probabilities are fixed. So is it a binomial experiment? Yes, it is. So this is the most common binomial distribution example. And we can write this way here. If x is, x here, we can write it as the number of heads, or we can say number of tails, depending on the question. So here the number of heads, sorry, in the question it says we want to find the number of heads. So x will be then the number of heads. Now, some typical cases, most cases with the 2 probability or 2 outcomes can be taken as binomial distribution. Now, for example, testing and effectiveness, the effectiveness of a drug. So you take, for example, 100 patients, take the drug. So it means you give the drug 100 times, and each patient, you have 2 outcomes. Either the drug is effective on the patient or not effective. So n trials, n patients, each time there are 2 outcomes. So this is a binomial distribution. Now, monthly sales of a bicycle salesperson. So salesperson, it means like the person selling, okay, has many customers during the month. So the number of customers, let's say trials, and for each customer, the salesperson either makes a sale or doesn't make a sale. So it means like for each customer, he deals with a customer and he sells something or he doesn't sell. So we say selling, success, not selling, um, failure. So each customer can be treated as one trial, and each outcome is failure or success, selling or not selling. Now, test for 2 drinks. So 10 people are tasting 2 different drinks. So you can take each person as a trial, and uh, for each person there will be 2 outcomes. Either they will say this drink is good or the other drink is good. So they will make a comparison for 2 drinks. And so they will choose the first drink or the second drink, their favorite. So there will be 2 outcomes for each customers or for each person. Now, quality inspections in a company testing 100 manufacturers part. So you can take the 100 manufactured parts as the trials, and for each part, the quality inspector decides whether this part is defective or not defective. Defective. So it has 2 outcomes for each part. So each part behaves like trial, and it makes a binomial distribution. So these are some binomial experiments from the real life. Let's look at this example. 75% of students at a college with large student population use the social media site Facebook, and 3 students are randomly selected from this college. What is the probability that exactly 2 of these 3 students use Facebook? Now, when you choose, okay, here you can take this one as like one trial as a one student here. So when you ask a student, so you have two outcomes here for a student. So it means he is using using Facebook, or not using Facebook. Now, what is the probabilities here? So it says 75% of the students in the college use Facebook. So it means the probability here using Facebook probability, you can say it's 0.75. And what is the probability of not using it? It's 1 minus p, which is 0.25. So the question is, what is the probability that exactly two of these three students use the Facebook? So here, we have a binomial experiment here. Binomial experiment. So in this case, we have a binomial distribution, and we can define x. What is x here? It says exactly two of these three students use Facebook. So we can say x is the number of students using Facebook. Now, since this is a binomial experiment, so x has, okay, now the success here is using Facebook then. Your success here is using Facebook then. So x will have the binomial distribution then. How many trials we have? Three students. Our trial numbers are student numbers. And success we're using Facebook will be just 0.75. So we have this binomial. So the x has binomial distribution. So then we can answer the question now because we know the formula for such variable. So what is the probability that exactly two of these three students use Facebook? So we are trying to find what is px equal to 2. So if you remember the rule, this is 3 choose 2 times 0.75 to 2 second power times 0.25 to 3 minus 2, so which is first power. So you can say this is equal to then, and this is when you calculate it will be 3 and 0.75 squared times 0.25, which makes equal to 27 over 32, maybe something like this. Okay, let's see the answer. In an airport, 5 radars are in service and each has probability of 0.9 to detect an arriving aircraft. Radars operate independently of each other. Find the probability that an arriving aircraft will be detected by at least 4 radars. Now, let's try to understand the situation. There are radars, and for a radar, we have, okay, if there's a plane approaching, then there are two possibilities. Radar detect or not detect the airplane. So it says that the probability detecting is 0.9 and the probability for not detecting is then 0.1 because 1 minus 0.9 is 0.1. I write the failure here, the probability of the failure or not detecting. Now, we can view each radar, each radar is dependent of each other. So then we can take this one as a trial here. Our trials are radars. Now each radar, each trial is independent. Each radar independent. They work independently, so they do not interfere with each other. So in this case, this is a binomial experiment, and the radar number is fixed. It's the 5 radars. This is a binomial experiment. Now, what is x here? It's x, the random variable x. So it's asking the probability that an arriving aircraft will be detected by at least 4 radars. So we can take this one, the random variable, as the number of radars that detect uh, the aircraft. Now, so since this is a binomial experiment, so this x has a binomial distribution. Now, detecting the aircraft is the success for x, so its success probability will be 0.9, and the number of trials is 5 because we have 5 radars. It's 5 then. So x has a binomial distribution with 5 trials and 0.9 probability of success. Now we know x has this probability distribution. Now what is it asking? It's asking what's the probability that of these 4 radars are detecting the aircraft. So it's asking what's the probability x is bigger than 4. So the probability bigger than 4, it means the probability of x equal to 4 plus the probability of x equal to 5. So the only thing left here is to find these two probabilities, and the important we know is the most important, the very obvious thing is it has a binomial distribution, and we have a formula for it. We can find these probabilities easily by using the probability function of the binomial distribution. Now, let's see. We did the hardest part, and the rest is just to apply the formula. Okay, I'm going to show how to apply the formula here. X is the number of radars that detect the aircraft, and the number of trials are n equal to 5, 0, 9, and 0.1. And we have shown this binomial distribution. So we use the formula for binomial random variable. You can check the formula. Your n is 5, the little x is 4. We write here 4, 5 minus 4. This is for 5. We have this 5, 5, 5 here, 5 minus 5. You can calculate these and you will get the probability as 0.9185, not 0.9185. Now let's look at this example here. Suppose that 70% of the students drink coffee at breakfast and the others drink tea. We select 4 students randomly and independently. Answer the following questions. What's the probability that none of the 4 students drink coffee? And one of 4 students drinks coffee. 2 of 4 students drink coffee. And 3 of 4 students drink coffee. And at least 1 student drink coffee. Now, it's always asking the number of the students, drinking coffee. Now, let's do some observation here. When you pick a student, he has 2 options. I mean, he can say, I drink coffee. There are 2 possibilities. He drinks coffee or drinks tea. So with the probability, it's 0.7 here. Why it's 0.7? Because 70% of the students drink coffee at breakfast. So it means when you choose a student with 70% probability, he's drinking coffee. And drinking tea is the rest, so it has to be 0.3. And you can think a student, choosing a student is like a 1 trial here. And if you choose a student, you have two outcomes, and each student has we assume they're independent of each other, so they do not affect each other. So they're independent on their choice, let's say. Now, in this case, and how many students we asked, so we have 4 trials, 4 students, it's fixed. So this is a binomial experiment with 4 trials. Now, then, okay, what is it asking? The number of students. So that you have to say what's your random variable. X is now, your X is number of students drinking coffee, who drink coffee. So since it's a binomial experiment, you can directly say X has a binomial distribution. Now, what kind of distribution? It's X as a binomial distribution. So how many trials we have? 4 trials. So because we have 4 students here, and what's the success for X? Drinking coffee is the success. So what's the probability of drinking coffee? It's 0.7. Now X has this probability distribution. Now the rest is very easy because you want to find here the probability that none of the 4 students is drinking coffee. It means what's the probability that X equal to 0? What's the probability of 1 student drinking coffee? It means like X equal to 1. 2 students drinking coffee, the probability that X equal to 2, and the probability that X equal to 3 here. And it says at least 1 student. It means the probability here, the probability that X is at least 1 or X bigger than 1 or equal to 1. And we know this one. And to find them, there's a formula to find the probability for each case. We can use the formula for the probability. Now, let's look at here. I mean, the first thing is you have to make this observation first. This is what I told you. And now the rest is easy. So it's asking none of 4 students drink coffee. It means Px equal to 0, and use the formula. Put 0 and 4 here, and then you'll get it. And now one of the students, it means Px equal to 1. And then the other thing is Px equal to 2, and use formula. And 3 students out of 4, so it will be x equal to 3. Now you use the rule, the formula. At least 1 student means like x is bigger than 1. So then x is bigger than 1 means 1 minus the probability of x less than 1. In this case, the probability, we're talking about the probability of x equal to 0, and it means this. Or another way to do it is like px equal to 1 plus px equal to 2, px equal to 3, and px equal to 4. This is another way of calculating this, but this is too long, and it's better we use the complement here. But if you also calculate this one, this is equal to this probability. Now let's look at this the other example here. Suppose 70% of the students like to play basketball. We selected 4 students randomly and independently. Answer the following questions. It says at most 2 students. What's the probability that at most 2 students play basketball? And what's the probability that at least 2 students play basketball? So here, uh, when you choose a student, it's like a trial now. The student likes, there are 2 choices here and 2 um, possibilities. He likes to play basketball, and the other one is doesn't like basketball. Okay, so each student is like a trial here. One trial is like one student here, and we have two outcomes for each trial. And what are the probabilities of liking basketball? So it says 70% of the students like um, playing basketball. So it means when you choose a student, it's 70% possibility he likes basketball. And what's the probability that he doesn't like? We know it's 1 minus 0.7. So this is I need 1 minus 0.7. And then we know them. So it's asking how many students play basketball or like to play basketball. So since this is asking about the playing basketball, I will say X is here the number of students playing basketball. Now here, then this is a binomial experiment here, binomial experiment, and its X is then has a binomial distribution, and there are four students, so it will be four trials. And for X, what is the success? Success is playing basketball. So you say, you put here 0.7. Now, once you get this one, you can find the probability of X equal to 1, 0, 2, 3, whatever it is. I mean, what is asked, we can find it. Okay, now, so it says at most 2. It's asking what then? It's asking what? It's asking at most 2 means Bx, at most 2, and at least 2, it's at least 2. So now we can use the formulas and we can get it. So it corresponds to Px less than or equal to 2, so it makes 0, Px equal to 0, Px equal to 1, Px equal to 2. And the other one is at least 2. It means Bx is bigger than or equal to 2. It means like 2, 3, and 4, they are sum. For each one, we have this formula, and then we can calculate it with a calculator and get the result. Now, let's talk about the mean and the variance and standard deviation of a variable that has a binomial distribution. And okay, now here we can say this X is, let's say, a binomial distribution, B and P. Now, the mean of X here will be equal to mu, which is n times P, and the variance of X, the variable X, is n times P times Q, and its standard deviation for X is square root of npq. Now let's look at this example. A die is rolled 360 times, and it says find the mean and the variance and standard deviation of the number of fours that will be rolled. Now, each rolling seems to be a trial, so it's rolling and is a trial here. So we do it 360 times. Now, each roll, okay, we are looking at what X here is the number of fours that are rolled. So each roll has two outcomes, let's say. We can divide it into two, like either it will give you 4 or not 4. So if you do it this way, then this becomes a binomial experiment. Indeed, it has, a roll has 6 outcomes, but you can view it as this way. It's either 4 or not 4. So what's the probability here? The getting 4, it's 1 over 6. But what is the probability getting not 4? It's, you can say 1 minus 1 over 6, which is 5 over 6. So now you can say X is, as a binomial distribution, how many trials or rolls we have? 360. And so it says the number of fours that are rolled. So 4 will be rolled. So the success will be 1 over 6. So we have this one. Then the rest is easy. Now here, n is what? 360, and p is 1 over 6, and q is 5 over 6. And we can find the mean, the variance, and the standard deviation because we have their formulas. Okay, now we understood how to establish x and how to see it's a binomial distribution. Now we know it, so we can do the rest because the rest is all about using the formulas here. So since if you got this one, then the rest is easy. So it will be n times p, the mean. Variance is np times q, so this is npq. And the standard deviation, of course, it's square root. So we got this one. Now let's look at this example. In this example, this is too easy because it already gives x is a random variable with binomial distribution with 5 trials, and 2 over 3 is the probability success of the probability of the success. And it's straightforward here. This n is given, p is given, and you can find q is like 1 over 3. And now you can find the mean and the standard deviation by using the formulas. If you remember the formulas, the mean is n times p, which is n is 5 here, and p is 2 over 3. So you multiply, you get this one, you get the mean. And the variance is n times p times q if it's a binomial distribution, and you know these. And you put them here, and you got it. And then the standard deviation is the square root of the variance, which is 1.054. 1.0054. Now let's look at this example. Here in this example again, you have to see it's a binomial distribution, and you have to find the random variable and what is success, what is failure. Now, a basketball player makes 80% of his free throws, and in a game he takes 3 free throw attempts. Okay, now find the mean and the variance of, okay, this is missing here, of his success. Okay, now successful throws, let's say, full throws. Now it's okay. Now here, each free throw, you can take it as a trial here. And it has 2 outcomes, successful or not. Now, here, this sentence is saying he's making 80% of his free throws, means his successful rate is 0.8. So not successful means, okay, it will be here, I guess there's no 2L. Okay, so this was 0.2 then. Now, this is a binomial distribution. Now, x is what? X is successful. X is what? X is the number of successful rows. So successful rows. I'm not sure it's the L, 2Ls. Okay, anyway. Now, the number of successful rows. Then x, this is a binomial distribution, binomial experiment, right? Because each throw are independent of each other, and we have 2 outcomes with constant probabilities. Now x is a binomial behavior, and the number the number of um, the trials. So how many throws we have? Three. So three. So the experiment is making three throws, and then he wants the successful throws for x. So success for the x is successful throws. So it's the probability is 0.8. Now we know this one. Now this is n. This is P, and Q usually is 0.2. And you can find the mean and the variance now. This is easy. Now this part, the only difficult part is this part. I mean, when you write this part, the rest is easy. The rest is just using the formula here. But here, let me also put this one here. This is important because you have to know the random variable here. What is the variable? So we are given NPQ, and then we can use the mean n times p, and the variance is np times q, and we have these numbers. Now let's look at this example. 15% of the devices produced by a computer hardware manufacturer are defective. If we order 150 such devices, find the mean, variance, and the standard deviation of. Okay, now we have to say what is the variable defective devices. Okay, devices of the number of defective devices, I will say, of the number of defective devices. Now, okay, we take a computer device. Okay, let's say device. We have a device here, and when we take a device, we have it's a defective one or not defective, and we will treat each trial as each device. So each device has 15%. So if 15% of the devices are defective, so it means when you take a device, its probability being defective is 0.15. And now, what is the probability of not defective? It will be 0.85. And okay, now we are trying to find, we ordered 150 devices. So this is a binomial experiment, and each device is independent of each other. So the number of trials here is 150. Now what is X? X is the number of defective devices. Now, since the experiment is binomial, so X will have a binomial distribution. Now, how many trials are there? How many devices? It's 150 devices. And being defective is the success here, so this is 0.15. I mean, for X, we are looking for defective devices here, so it means defective being the success here. And the failure is 0.85. So we have this distribution. So X is a binomial distribution with 150 trials and 0.15 probability. So now we can answer the mean and the variance and the standard deviation question because we made the hard part. Now the rest is just using the formula. So X, okay, the defective devices, and you can say N. Okay, we got this observation. Now the rest is easy. The mean is like n times p, and the variance is n times p times q, and standard deviation is the square root of the variance, and that's it. Now we will solve the worksheet problems. Which of the following is false for a binomial distribution? Now, the random variable is discrete. Yes, it takes the values x equal to 0, 1, 2, 3, and depending on the experiment, but they're all countable and discrete. So each variable, each trial is independent. So in a binomial distribution, we have trials that are independent, and each trial has two possible outcomes. Yes. So obviously, this is the false one. We are assuming sampling without replacement. I think here it assumes in each trial we can do replacement if you're choosing a ball. No, this is not true. If you do without replacement, then um, the trials will be dependent. So for this reason, it cannot be A. Suppose 20 donors come to a blood trial. Assume that the blood donors are not related in any way so that we can consider them independent. The probability that the donor is O blood is 0.06, and which is constant from donor to donor. Let X be the number of donors donors who are O blood. What is the distribution of X? Now each donor we can say has O blood, so we can think this one as um, having O blood and having not O blood. So we can think of these two outcomes for each donor. So it will be, and the donors are independent of each other, and we can think the donors as the trials here, and we have 20 donors here. They're independent of each other. So this is, we can take this one as a binomial distribution or binomial experiment. And X be the number of the donors that are O blood, so it means this is success. Number of donors, number now here the probability of this one is 0.06, and now of course it will be then 0.94, and 1 minus 0.06. So X has, okay, if it's a binomial experiment, if X is the number of the success, here the success, and it means like having O blood. So X has a binomial distribution with 20 trials, and the success probability is 0.06. So it has to be A. Suppose we have a random variable x where p x equal to k is equal to 15. Choose k times 0.29k and 0.7115 minus k for k equal to 0, 1 up to 15. What is the mean of x? Okay, if you remember, the mean of x is this. And to find this one, we have to like x and px, and here k is 0, 1, 15, so x can take the value 0, so we will find p0 and 1 times p1, so we will do it up to 15. So this is generally, I mean, in discrete probability distributions, this is how we do it, if you remember. but this is too long here. We will not do it this way. So instead, we will look at the probability distribution, the probability function here. Um, if pxk equal to 15 choose k times 0.29 to the kth times 0.021 to the 15 minus kth power, and for k is from 0 to 15, this probability distribution, this probability function here is telling x has a binomial distribution, with 15 here is just the number of the trials, and kth power is, here is kth and there's k here, so it says the success probability 0.29. So you can say this, x has a binomial distribution, and now if it's binomial distribution, so the mean of x we know in a binomial distribution, no need to do this long calculation and find this one. Instead, we can directly say it's 15 times 0.29, so which is about 4.35. If x has a binomial distribution with 20 trials and a mean of 5, what's the success probability p is what? Okay, if x has a binomial distribution, then we can write this as a binomial distribution with 20 trials, and let's say p success, the p is the probability of success. Okay, we write it this way, the p is the probability of success. Now in this case, we know the mean of x is n times p here, so n is 20, and p is, we don't know it yet, but mean is given here, it's 5. So here we see it's 5 over 20, so which is 0.25. A die is rolled 72 times. Find the mean standard deviation of the number of twos that will be rolled. So a die is rolled and 72 times. So let's see, it's asking the mean and the standard deviation of the number of twos. So here our random variable is the number of twos. When a die is rolled, dice is rolled 72 times. Now the important thing is we have either 2 or not. So here you can, when you roll a die, you will get 2, okay, and the others. So here 2 is just the probability here is for each roll, it's 1 over 6. But the others, the probability of getting the others is 6 over 5. So you can think of this one with 2 outcomes, 2 or not. And each rolling is independent of each other, so you can think of it's a trial, a die, rolling a die. Once is a trial, you have 2 outcomes, and each trial is independent. And each time the probabilities are fixed here. So this is a binomial experiment. So x has, so the x is the number of twos, which is, we say, success here. So we will accept having 2 is getting 2 is a success. So X will have the probability, the binomial distribution with n trials, which is 72 trials here, 72 rolling, and the success is 1 over 6. Now, we know that if it's a binomial random variable, then its mean is 72 times 1 over 6, which is 12. And and its standard deviation, okay, this makes 12, so I will say this is either this one or this one is the correct answer. Now, let me write what is standard deviation. Standard deviation of x is square root of the variance, which is n times p times q, if you remember. So what is n? It's 72. What is p? It's 1 over 6. And q here, if you know, all the time, like q is 1 minus p, and here q will be 1 minus 1 over 6. So it's 5 over 6. Now, if you do this calculation, there will be cancellation, and you will get square root 10. So standard deviation has to be square root 10. So the correct answer is B. Now, compute the probability of x equal to 5 successes using the binomial formula. Here, the number of trials is 10 and p is 0.73, so the probability of success, I guess. Now, you can say x has, okay, it says use the binomial formula, okay, and x has the, since we will use the binomial formula, it means it has binomial distribution. Here, n is 10 and p is 0.73. And the probability that Px equal to k is C 10 choose k times 0.73 to the kth power times 1 minus 73 to the kth to the 10 minus kth power. So this is the probability of failure. This is the probability of success. Now it says, what is Px equal to 5? So when you calculate this one, this is 10 choose 5 times 0.73 to the 5th power times 0.27 to the, okay, here when you put here 5, you will get 10 minus 5, which is, I will say just 5. Now, we will calculate this one. So you can use a calculator to find this. This one will be 252 times 0.0.0.29, or I will say 0.3 approximately. And when you multiply them, this is approximately, okay, I do some rounding, so it will be 0.075. Approximately 10.3% of American high school students drop out of school before before graduation. So it means they stop coming to high school. They don't finish the school, they leave. Choose 10 students entering high school at random. Find the probability that no more than 2 from these 10 students drop out. Now, if you want to say a random variable, here's x, you can say the number of the students who drop out from these 10 students, from 10 students, 10 chosen students. Now we want to find the probability that x is less than, okay, no more than 2 means we want it less than or equal to 2. So what is this? So we have to find the probability distribution for x. Now here, if you choose a student, we have two options for him or her. One, he will drop out, or not drop out, won't drop out. So it says 10%, 10.3% of American students, high schools drop out of school. So it means the possibility is 10% to drop out. The possibility of dropping out is 10.3%. Now, what's the possibility that it will not drop out or she will not drop out? It's 100 minus 10.3, which makes 89.7. So we assume they're independent of each other. The students, they do not affect each other in dropping out the school. So we can treat this one as a binomial distribution. Now each trial here is a student. We are choosing 10 students here. So the number of students here we chose is 10. So this is the number of trials here. This is important. Now this is a binomial experiment. So now you can say the number of students dropping out from 10 students chosen is x, has this binomial distribution 10 trials, each with 10.3% probability. So it means it's 0.0, sorry, this is 103. So since we know x has this probability distribution, we can write this one. Okay, we can use it here. So what is the probability x less than or equal to 2? Either x equal to 0 plus either x equal to 1. You know, it always starts with 0 in the probability in the binomial distributions, and px equal to 2. So we have to calculate each probability by using this, by using the formula here. The formula for the probability x equal to k is, if you remember, it'll be n choose k times probability of success to the k power and the probability of failure minus n minus k. So we have to use it here. So in this case, if you write the formula here, 10 choose 0 times 0.103 to the 0th power times what is the failure? It's 0.897 to the 10th power. Okay, it's better I get some space here. Now the only thing left is like to use the formula, so I will just use the formula for each. So this will be, okay, just it will be, okay, 10 choose 0, 10 choose 0 times 0.103 to the 0th power times 0.897 to the 10th power. So this is corresponding to b x equal to 0, the probability of x equal to 0, and then plus. Now we will write this one, the formula for this one. So it will be 10 choose 0, 10 choose 1 times 0.103 to the first power times 0.897 to the 9th power, and then plus for this one we'll get 10 choose 2 times 0.103 squared times 0.897 to the 8th power. Then if we use a calculator and calculate this, we'll get equal to 0.925. Okay, when you round it, it will get 0.925. A lab network consists of 5 computers was attacked by a computer virus. This enters each computer with probability 0.4 independently of other computers. A. Find the probability that the virus enters exactly 3 computers, and find the probability that the virus enters at least 1 computer, and find the mean, the variance, and the standard deviation of number of computers. The number of computers the virus enters. Now, in order to solve this problem, we have to know what is the random variable here, and the random variable, what's the probability distribution of the random variable. So x here is, as you see, the virus enters 3 computers. It says virus enters 1 computer, at least 1 computer. So you can say the x is the number of computers the virus enters. Now, what can we say about the probability distribution of x? Now, let's think it here. Okay. Now we have computers, so each computer has can be infected, or I mean the virus will enter it or not. So I will say here the virus enters. Oh, so it's attacked by the virus or not attacked. So virus enters or virus does not enter. So the probability each time we assume it's 0.4, and here it's 0.610. Now they're independent. The computers independent in taking the virus. I mean the virus attack for the attack of the virus. They are independent. They are not connected to each other. So you can think this each trial is like a computer here, and we have 5 computers, and these are the number of trials here. 5 trials. Each has this probability 0.4 virus attack, 0.6 has not attacked or not infected. Now, if you look at this one here, this is a binomial experiment. You can view it as a binomial experiment here. If it is a binomial experiment, so x has a binomial probability distribution. So the virus, how many computers, or how many trials we have, 5. And the virus enters, here it says the number of computers the virus enters, it's 0.4. And so the probability of success, success is defined by entering the virus in this variable. So the probability is this. So now we know X here is the number of computers the virus enters or attacks, and the other one, the X, has the binomial probability distribution. Now we know it, then we can do the rest according to this information. The rest is just applying the formula for the probability of a binomial random variable. So here it says the virus entered exactly 3 computers. So the number of the computers attacked by the virus or the virus enters is 3. And so what's the probability of X equal to 3? So X has a binomial distribution, so we use the formula for it. So 5 choose 3 times 0.4 cubed, and then the failure will be, okay, not attacking 0.6 to second power here. All these exponents have to add up to the number of trials, which is 5. Now then we can calculate this one. Okay, I will do the calculations at the very end. Now the probability that the virus enters at least 1 computer, so it means the probability that X is bigger than or equal to 1. Now in this case, we might have P X equal to 1, when we will get 1, 2, 3, 4, and 5. No, it will take a long time to calculate this one. So for this reason, it's better I go with the complement. So instead of this, since the sum of all the probabilities is 1 in a discrete probability distribution, so I will just use it as, I will use the complement here. It's 1 minus px less than 1. So I will say this is 1 minus px equal to 0 then. So I can use the formula for this one. And the mean, the variance, and the standard deviation of the number of computers the virus enters. Now for this one, since we have a binomial distribution, and the mean of X here is clearly n times p, which is 5 computers times 0.4, so p here. So it will be just 2. So it means the expected value of the computers got infected by the virus is 2. Now the variance of X is n times p times q, which is 5 times 0.4 times 0.6, which is 1.2. And okay, and the standard deviation of X is just square root of npq, which is square root 1.2. Now let's see. Okay, what are these values? 0.2304, or you can just say like 0.23. If you round it, if you cut this part. Now the probability of 1 minus px equal to 0, we will use the formula here for this one. Okay, I will just erase this part. Anyway, just computation now. I will erase this part and do the computation here. Px equal to 0 is 520 times 0.4, 0 power times 0.6 to the 5th power. And this makes 1 automatically, and this makes 1 automatically. And this one makes, now it is reported that, so it is reported that, I will say, not if, it is reported that 77 of the workers of age 16 or over drive to work alone. So choose eight workers at random. So find the probability that all drive to work alone and the probability that exactly three drive to work alone, more than or equal to one drive to work alone. So the mean and the variance and standard deviation. Okay, we have to say what mean these. In this question, so we are asking the mean of the number of workers, um, number of workers who drive to work alone. Uh, yeah, and here um, in eight workers, let's say, among eight workers here, among eight workers. Now this is the same. Now, okay, what is X here, the random variable? So it's asking like all drive to work alone. So three drive to work alone. So that should be the number of, X will be the number of the workers. Okay, I don't want to write a lot. I just say workers. Okay, who drive alone. Okay, who drive to work alone. I will say this, alone. Now, in order to answer these questions, we have to know the probability distribution of X. Now, if you choose a worker here, I mean, if you choose a worker, then this worker will have two options here. It's driving home alone, driving to work alone, sorry, drive to work alone, or doesn't drive alone. So it has two options, and here, what's the probability that he drives alone? So this data here, it's showing, it says 77% of age 16 or over drive to work alone. So I will take it as 0.77. And then who doesn't drive? The worker doesn't drive alone. The probability will be just 1 minus 0.77. So I will take 23. And the workers are independent of each other. So I will assume this one. And since they're driving alone, so I mean, okay, they're independent, I will say. And each trial is like a worker here. Each trial is worker. So when you look at this one here, X, the number of the workers who drive alone. So driving alone is the success here. So X has, this is a binomial distribution then, I mean binomial experiment here. We will assume this is a binomial experiment. So since it has two outcomes and we assume the workers are independent of each other in driving home, in driving. So then we have X, the number of trials, the number of workers chosen, it's 8. This is 8. And the probability of driving alone is 0.77. So we'll get this one first. Okay, X here is as a binomial distribution with 8 trials with the probability of success 0.77. So now we can read the questions this way. What is the probability that all drive to work alone? So it means like X equal to 8. So the probability that X equal to 8. Now if this is a binomial distribution, so we can say this is 8, choose 8 times 0.77 to the 8th power times 0.23 to the 0th power. You know, they should add up. That's 8 plus 0, it has to be 8 here. The number of trials, sorry, is 8. Now the probability exactly 3 drive to home, try to drive to work alone will be uh, 8, choose 3 times 0.77 cubed times 0.23 to the fifth power. So as you see, 3 plus 5, it's 8. Now the probability more than or equal to one drive to work home to work alone, more than or equal to, more than or equal to. So again, like in the previous one, it's better to go with the complement here. This will be 1 minus x bigger than 0, because otherwise I have to write px equal to 1, 2, 3, 4, 5, up to 8. So to use the complement here, it's a good option here. And now, when it comes to, okay, we know x now, what it is. So I will just erase this one. Now it's asking the mean of x. The mean of x is n times p, which is n is 8 times 0.77. So the variance of x is n times p times q, which is 8 times 0.77 times 0.23. And the standard deviation is like the standard deviation of x is like square root np times q, which is 8 times 0.77 times 0.23. Take the square root. Now, okay, let's look at here. Okay, let's try to find these. Let's calculate them with a calculator. This will be 0.124. Okay, I rounded the last part here. Okay, and then the other one, 0.016, if I'm not wrong. And this one will be 1 minus 820 times 0.77 to the 0th power times 0.23 to the 8th power. If you calculate this one, we get 0.999, and there are some more nines here, but anyway, I will stop here. Okay, and these are, okay, you can do them by yourself, so I will just leave them to you. Okay, find them. Okay, calculate them. This is easy, you can do it with a calculator. A multiple choice exam is composed of 10 questions, and each question consists of 4 possible answers such that only one is true. And the student chooses randomly an answer for each question. Find the probability that he has exactly 5 correct answers, at most 9 correct answers, and 2 correct answers. Now, let's try to understand the situation. There's a multiple choice exam. There are 10 questions here. Question 1, question 2, and it goes up to 10. In each one, there are 4 possible answers like A, B, C, D. And one of them is true, and so okay, one of them is true, and the choosers the student chooses randomly an answer. Okay, now this is randomly, so he's not reading the questions. Okay, now find the probability that he has 5 correct answers. Now, from the questions here, you can understand it's asking what the exactly 5 correct answers and 9 correct answers. So if you define x, the random variable, it's asking the number of correct answers in the test. So it means in the test, the exam. So exam is 10 questions, by the way. Now we have to find the probability distribution formula for x. Now let's try to understand. If you choose a question, like think of a question here, You answer this one correct. Choose the correct answer or wrong. So there are two possibilities for each question. Now, and how can you find the probability of answer choosing correctly? Because since I'm doing it, I mean, we are doing it randomly. The student does it randomly. So how many options does he have? A, B, C, D, four options, and one of them is correct. One in four is correct. Correct. So the probability of answering a question correctly is 1/4 because one of them is correct out of four, and the probability that he's not is answering it wrong is 3/4. So each question is independent of each other. So we can assume this is the trial here. Answering a question is a trial. And how many trials we have? We have 10 questions to be answered. So we have 10 trials here. 10 trials because 10 questions here. And the questions are independent of each other. So for this, I mean, we assume it. So I mean, it doesn't say directly, but okay, it doesn't matter because he's not reading the questions at all. I mean, so for this reason, this is a binomial experiment. So X here, the number of correct answers in the exam is, so X will have the binomial distribution with how many trials? 10 trials because 10 questions. And the success here is the correct answer. So what's the probability of choosing a correct answer? It's just 1/4. So X has the binomial distribution. Now, since we know it, the rest is just very easy. So I'll erase this part. So we know these two things. This is very important. Now, he has correctly 5 answers. So it will be equal to the so we will, if since it's binomial distribution so we have a formula for the probability. It's 5. Sorry, it's 10 questions, 10 choose 5 times 1/4 to the 5th question times the probability of wrong answers, choosing wrong, 3/4 to the 5th power. So you know they will add up 10. So we will find this one, and then he has at most 9 correct answers. So it means the probability that X is less than or equal to 9. So it means, okay, we can do it with 1 minus p x bigger than 10, so bigger than 9. So this has to be equal to 1 minus the probability that x equal to 10. So having all answers true. And at least 2 correct answers, what's the probability that at least 2? It means like px, sorry, just at most 2. So it has to be at least 2. It has to be x bigger than or equal to 2. And okay, let's try to write this one. Now it will be 2, 3, you know, then it will go up to 10. So it's a long job to calculate this one. Okay, let's try to use the complement here. So if you do the, okay, if you use the complement, this is the 1 minus the probability that x is less than 2. So in this case, it's easy to calculate this part because it can be 0. I'll say this plus the probability x equal to 1. So just we can calculate only 2 and that's it. Okay, let's look at this one here. What is this equal to? So you can use a calculator and find it. This is equal to 0.05 8, if I'm not wrong. So, and let's look at the others. This is 1 minus, this one is 10 choose 10 times 1 over 4, 10 power over 3 over 4 to the 0th power. And this will give you, okay, I will just write the answer here. This will give you just 0. I think it will be 0.999, something like this. Yes, so you can say it's 0.999. And when it comes to this one, the last one, this will be 1 minus, okay, let's write the sum here. The probability that x equal to 0, this is 10 choose 0, times 1 over 4 to the 0th power, times 3 over 4 to the 10 power, plus and choose 1 over 4 to the first power, then 3 over 4 to the 9th power. So we have to calculate this one. And the whole thing here is, it turns out it's 0.756. Okay, it's around this. So it means in a 10 question test exam, the multiple choice exam, if you do it randomly, the probability that at least you have two correct answers is 75%. And I think that's it.